Good evening, everyone. My name is Carlos. I come from the University of California at Santa Barbara. Um, the interest or the topic of this paper is about healthcare and computer vision applications for healthcare. Um, the problem, I was looking for techniques that would help healthcare overall. So, talking to medical doctors, they suggested to look into the ICU. There's 5 million people that go to the ICU. 46% of them are elderly. Um, the national cost annually is about 100. It's now about 130 billion dollars, and it's going up by 5 billion every year. The average duration, the average stay of a patient in an ICU is about 9 days. Mortality rate, just by being accepted, is 10 to 30%, depending on your conditions. And it increases by 7% per day that you are in the ICU. So the longer you stay, the higher the risk. The 2020 estimates are that the elderly population, the ones that require the most resources, will increase by 69%, while the number of caretakers will decrease by 35%. So I'm going to try to address some of the questions. Why the ICU? Of course, there's this. This is a strategic location where whatever therapies are developed can be transferred to all the other units because all patients from all the other units come to this location. What are some of the problems? I'll be going through them. And as a community computer vision scientist, what can we do to help? So one of the problems, one of the pathologies is sleep deprivation, or also known as sleep hygiene. Pretty much the problem is that if you have a bad night's sleep and you're already in the ICU, that increases your stay, which will increase your mortality rate. There's strong correlation. This is all observational, as most of the health therapies are. Sleep poses correlate to the quality of sleep. The only ways that are the current technique to measure this are obtrusive measurements such as the polysomnogram. This is an illustration of that. So it's a machine that is connected to you. The second pathology is the cubitus ulcerations, pretty much bed sores. There's 2.5 million occurrences, 80% happening in the ICU. It's caused by bony areas on patients that are in the same position for an extended period of time. It is measured using the Braden scale, which is very observational and subjective. And this is an illustration of what they look like. This can be preventable. So if anyone has worked in healthcare, it is very difficult to collect data. Almost impossible because of privacy issues, because FDA. So we created this mock-up intensive care unit room on campus. We created this box with sensors, pretty much depth cameras. This is just a little bit of the ones that we have. We have a bunch of room sensors that measure illumination, temperature, sound. And the idea is that these have to be self-contained, self-powered. They cannot disturb the infrastructure of an ICU. To try to address these problems with poses, we collected the best to our knowledge what it would be an ideal scenario. And we tried basic techniques, the formal part models and Kinect API. There were some assumptions, and of course some case failures, mostly clutter, minor occlusions, and of course the lack of depth contrast. So what is the problem? The problem is we have this dictionary of poses that we're trying to classify. We have these multiple inputs from RGB, from depth, and from a pressure mat. That deployment is very difficult because it will be in touch with the patient. The idea is that now we have this query, and each of them will be classified. Sorry, something changed with Google Docs. So each of them will have some sort of candidate. You're trying to find the best candidate for it. But the problem is that ICU is not a natural scenario. You have a bunch of changes in illumination. You have occlusions. So now what we do is we put a bunch of different views, and the idea would be to eliminate the sensor that is in contact with the patient. So we create this massive dictionary of data. We have all the data available online. And extract features, basic engineered features, histogram of oriented gradients and geometric moments. We come up with this couple constraint least squares, pretty much solve a bunch of optimization problems at once. If you want more details about how these elements are constructed, you can come to poster 17. These are some results. And the conclusion, of course. The idea is that it's promising.